right, so this is Mrs. Vandal again with a part 2 of section 16.5 and 16.6. We were talking about different ways to calculate delta G, gives free energy. And the first way we found was finding it through the delta G equals delta H minus T delta S. And then we calculate the problem and we found out that yes, indeed, it was spontaneous. Method number 2 is very similar to Hess's law. And if you remember Hess's law, it's like a puzzle that if you make the pieces work out, that if you need to manipulate the equation and flip the products and reactants around, you'd flip the sign around. If it multiply anything, it'd multiply the value. All that was from delta H way back when. And you do the exact same thing here with delta G. So let's take a look at this. If we want to convert diamonds into graphite. Now, let's see what happens. I have diamonds already on the reactant side, which is good, but I need to have the graphite over here on the product side. So what do I need to do? I need to flip these equations around. So if I flip those two equations around, what am I going to do with my delta G? I'm going to change the sign of that as well. So let's see how that works. So if I flip these two around, so I'm actually doing carbon dioxide is equal to C graphite plus oxygen, so delta G naught is equal to positive 394 kilojoules. And let's see how that helps. My carbon dioxides from my first and my second equation cancel out. My oxygens cancel out. And now I'm left with diamonds going to graphite, and that is what I want. So now just go ahead and add those three numbers together, and whoa, you get negative 3 kilojoules. That's not very big whatsoever. It's a very, very small delta G. It is spontaneous, but it's a pretty small negative number, and it will probably not go very far to the right before it achieves equilibrium. So it does work spontaneous, but it doesn't say for how long. Keep that in mind. And then finally, method number 3 looks just like what we've already done before. If I give you a chart of delta G values, you can do the same thing again. Hopefully this is starting to become old hat for you. Take the sum of the products minus the sum of the reactants. So in this case here, methanol is a high octane fuel used in high performance racing engines. Calculate the delta G naught for the combustion reaction of methanol given the following free energies of formation. Well, what do you think the very first thing we ought to do is we need to write down the balanced equation. So why don't you do that? Pause the computer here and wait and see what I... So before going on, did you get that as your balanced equation? Because you have to know that you have to get it right in order to keep working. So now that you have the balanced equation, hopefully you had it earlier, go ahead and solve for delta G. All right, so here is delta G. So the standard conditions is the delta G products minus the delta, or the sum of the G products minus the sum of the G reactants. So here I put in, I have 2 moles of the carbon dioxide. So I have 2 moles from the carbon dioxide times its value, negative 394 kilojoules per mole. We can do this again. Notice that I can cancel out my moles here. All right, the moles cancel out. 4 moles, which I didn't write down, can cancel out those moles. 2 moles, which I did write down, divided by those moles. So they'll cancel out. And when you do the math, I found my delta G of my reactants equal negative 1704 minus negative 326 kilojoules. And when you do your math, you get negative 1378 kilojoules. And because delta G is negative, yes, it is spontaneous. So I'll tell you what, why don't you do your summary on your own, and we will talk about it in class. See you tomorrow. Bye-bye.